So Khalees is going to start off with a lecture over spectroscopy and alcohols pretty soon. But other than that, thank you all for coming. And
okay, sounds good. If that's the case, then we'll just get started, and then people that are trickling in can catch up in a second. Okay, so first off, we are going to go over IR. So just in a broad, I guess, overview, what is IR spectroscopy? When you shine infrared light on a molecule, the molecule can then absorb energy from the light, and this energy from the light then causes the bond to stretch. And so this is called a stretching vibration, and it can be modeled by the oscillation of a spring. And so that's kind of an analogy that I'll bring up a couple times throughout this presentation. And by visualizing kind of a bond to a spring, then you'll be able to kind of understand these concepts a little more. So I would recommend trying to visualize that while we go through these slides. So if we're looking at the traditional IR graph, which I'm sure you guys have seen multiple times, on the y-axis is transmittance. And so in point A, where there is essentially 100% transmittance, this means that the light was transmitted to the sample and nothing was absorbed. And then in point B, where there's zero transmittance, there is nothing transmitted and the light was absorbed by the molecule, and hence the bond stretches and we get stretching vibration. And so that's just a little bit of the background if you never really understood what the meaning behind the transmittance was. Now if we're looking at the x-axis, that's where our wave number comes in. And so if we're looking at the actual units, the wave number is 1 over wavelength, and so that means our units are going to be 1 over centimeters. But since wave number is equal to frequency over the speed of light, we know that wave number and frequency of light is proportional, and so that will come in handy when we're looking at kind of the frequency later on. So when we break down the IR into two regions, there's basically a cutoff point at around 1500. And so below 1500 is what we like to call the fingerprint region. So this is going to be unique to each molecule. It is generally quite complex and it's harder to interpret. And so because of that, we don't typically look at a whole lot of signals within the fingerprint region. And we typically look above 1500, and so that's what's called the diagnostic region. And so we are then able to figure out the structure of the molecule and the functional groups based on the signals we see above 1500. So typically we just kind of not disregard, but we don't really pay attention as much to the signals that we see below 1500. So going more into what bond oscillation is, these are vibrations that only produce a change in dipole moment that are observed as signals. And something to note, I cannot see anyone's chats, so if someone is asking a question, I believe someone in the chat will answer that. So just to let you know. And then if we're talking about the factors that affect oscillation, there's two main things, which is the mass of the atoms as well as the strength of the bond. So if we're talking more about the mass of the atoms, the greater the mass of the atoms, the slower the vibrations or lower frequency. So if we look at the left, I guess, model, which models kind of a larger atom, in this case we can say it's like a carbon, then if you were to imagine two heavier objects, for example, like if there were two stones attached to a spring and you were to kind of like flick the spring, then it would move at a much slower frequency as to whether there were like two ping pong balls attached to the same spring. So that's kind of how I like to think about it in my head. And so therefore, the greater the mass of the atom, then the slower the spring will kind of oscillate and move back and forth. So more about the mass of the atoms. An equal mass distribution of atoms also leads to faster vibrations and higher frequency. So in kind of like the same example as before, if there were two stones, you know, there would be a lower frequency, but if there was a stone attached to a ping pong ball, that would then show like a higher frequency if the spring was kind of like hit. So now I want to go more into about the strength of the bond. The stronger the bond is, the more rigid it is, which then leads to faster vibrations and higher frequency. And so in this case, you can see that the single bond on the left-hand side would have a lower frequency compared to a double bond, which would have less of a frequency than a triple bond. And the reason for this is the stronger, you can imagine like if there are two springs, then it would be a stronger connection. And if you were to kind of hit it, it would vibrate a lot faster. And so that's just another analogy, I guess, with the spring that tends to work. More about the strength of the bond. A higher S character means electron density is closest to the nucleus, increasing bond strength. If you guys remember back to OChem 1 or perhaps even Gen Chem before that, we know that the s orbital is closest to the nucleus. And so that means that the more s character that a bond has, therefore the bond will be stronger. And as a result, then the frequency would be higher. So at the bottom it says sp bonds, or if the carbon is of sp, then it'll have 50% S character, and therefore the wave number is going to be around 3300. For sp2, which has 33% S character, that'll be around 3100, and then sp3, 25% S character, and that's around 2900. So a couple more things to know about the strength of the bond. So conjugation reduces double bond character, which then decreases frequency. If we're thinking about, for example, a benzene, your professors probably have mentioned the fact that each of the double bonds is actually kind of like a half double bond and half single bond because of the conjugation. And so it is continually alternating in a state where it's either a double bond or a single bond. And so because of that, each double bond is less strong than it would be if it was in isolation. And so since the bond is then essentially weakened, that causes the wave number and the frequency to be lowered. Similarly, so ring strain increases wave number. So having that ring strain would kind of strengthen and make that bond more rigid. And so because of that, the effect would be opposite, and we would have a higher wave number. And so that definitely comes into play when we're looking at the IR, because it would cause some readings that we would typically expect to be at a certain number to be slightly higher or lower. And that's just based on if there's conjugation or some ring strain within the compound. And so that's why almost all of the readings of wave numbers we give you guys are approximate. And that's only because conjugation, ring strain, and a couple other of factors can cause it to shift upwards or downwards. So now I want to go more into the exact wave number frequencies that you guys hopefully can recognize and take a look at when you're reading an IR. So if we're talking about carbon-carbon bonds, the highest you're going to see is around 2200, and so that's a carbon-carbon triple bond. And then if we're going lower on the spectrum, around 1660 is a carbon-carbon double bond. And kind of like what I just mentioned, because of the conjugation and the ring formation, even though there's less ring strain in a benzene, this causes the wave number to decrease. And so therefore, that's why the benzene, even though it is composed of double bonds, has a slightly lower wave number than the carbon-carbon double bond. So that's around 1600. And then at around 1200, we have the carbon-carbon single bond. Though I will say, because it is in the fingerprint region, we really don't pay attention to it as much, but just for your information. Now, if we're looking at the carbon-nitrogen bonds, at around 2200, there'll be the carbon-nitrogen triple bond, and they'll usually have a slightly lower transmittance, so it'll be a very large and kind of spiky peak. At around 1660, that's our carbon-nitrogen double bond, and then similar to kind of the carbon-carbon single bond, at around 1200 is where we're going to see the carbon-nitrogen single bond. If we're looking at, my bad, at around 3300, if we're looking at the carbon-hydrogen bonds, that's where we're going to see our SP. And then if we go slightly lower, at around the 3100 to 3000, that'll be our sp2 carbon-hydrogen bond. And then a little lower than that, our 3000 to 2800 range is the sp3 carbon to hydrogen bond. If we're looking at the nitrogen to hydrogen bonds, the more distinguishing factor here is kind of the number of peaks. And that has to do with kind of the symmetry of the nitrogen-hydrogen bonds. And so I won't go too much into that. But essentially, if there are two peaks, that'll be a primary amine with the nitrogen-hydrogen bond. And as we know, for primary amines, that means that there's one carbon attached, and there will be two hydrogens attached to that nitrogen. And then for one peak, our secondary amine, and so they'll be approximately in the same area, but the distinguishing factor to look for is definitely the number of peaks that are present. In terms of the oxygen-hydrogen bonds, this is the alcohols that you guys know. It definitely has a very distinctive peak, and it is very broad, and it has a round tip for the alcohol. And if we're looking at a carboxylic acid OH bond, then it'll have a broad signal as well, except the tip will look slightly different. So now I want to go more into the carbonyl bonds, and I want to break it up into each one because it can be slightly confusing considering that they all are around the 1700 range. But I just kind of want to break it down. So if we're looking at the carbonyl bonds, ketone shows up essentially by itself at around the 1715 range. And then if we're looking at an ester, esters will go slightly higher. So they'll be around the 1735 range. But as I mentioned earlier with ring strain, because the bonds are more rigid in a ring, that can cause the wave number to shift higher. And so if we're looking at like those three compounds at the bottom, depending on how much ring strain it is, it can cause it to increase quite a lot. And so in the most right compound, because there's only 4 atoms in that ring, and there's the angle is a lot smaller, like the 90 degrees, that causes a lot of ring strain. So that can be upwards of like 1818 for the wave number. When we're talking about carboxylic acids, the carbonyl group will be around 1710. But then, as I mentioned a couple of slides ago, there is going to be that OH group. And so that's going to be kind of that broad signal that you see in the around 3000, even slightly higher than that range. So it really depends, but that is a characteristic of the carboxylic acid. If we're talking about aldehydes, the carboxylic, or I don't know why this is carboxylic acid, I apologize, I meant to say carbonyl. So the carbonyl peak will be at around 1720, and then the carbon-hydrogen stretch will be around 2800 to 2700. And this kind of looks like fangs is what I always like to think of. And so they'll show up in that area, and that is one of the biggest indicators of the aldehyde because they'll have those 2 peaks in that area. Now, if we're talking about the amide, so the carbonyl peak will be around 1660. And then if we're looking at the 3500 to 3300 range, that's where that nitrogen-hydrogen stretch will show up. And so we're going to see like two bands. So that's indicative of the amide. So that's kind of the general overview of IR that I want to cover. And so now I want to go into the alcohol reactions. So first off, you guys will be using some of the reactions from OChem 1, and so we want to go over that and make sure you guys have a good grasp on those reactions because they will certainly come up. So first off, I want to talk about deprotonation of alcohols. And so this can be done in a multitude of ways using the ones shown here. So it can be like a strong base, a metal hydride, or a reduction by alkali metals. And so being able to deprotonate these turns them into good nucleophiles because OH by itself is not reactive. But once you have that negative charge on there, they become great nucleophiles, and then they can then attack other compounds and react. So in terms of forming alcohols, you can use hydrolysis of double bonds in order to form an alcohol. So as shown, that's the Hg2+, and then the water and the acidic environment. And another way to form alcohols is SN2 reactions to form the alcohol on the first degree and to form it as an electrophile. So that can be done in a number of ways. In here, there's the halides, so that can be these compounds as shown below. It can be benzylic, allylic, or just a single alkane chain with a halide attached. Another way to form alcohols is being able to reduce carbonyls. So that can be done with NaBH4 or lithium aluminum hydride. And so over here, you can see that there's ketones or an aldehyde that you start out with, and then reacting it with sodium NaBH4 can then form a primary or a secondary alcohol. And then below, the X is kind of representing that it could be a carboxylic acid, or you can put a halide there, or it could be an ester. And so then reacting it with lithium aluminum hydride can then form your primary alcohol. And then on the right side, nucleophilic attack on carbonyls with Grignard reagents or with lithium. And so those are kind of the two options that you guys have seen hopefully a number of times by now, I'm sure. And again, similar to before, you can start with a ketone, aldehyde, or as in the lower reaction shows, it can also be like an ester or something. And then you can then react that with your Grignard reagent or your lithium attached to whatever carbon chain you want. And then you can then form your alcohol. The one thing to note is that with your Grignard reagent, it will attack multiple times. So you will have that carbon chain or whatever compound you had attached multiple times. So just something to remember. So making alcohol a better leaving group is certainly important because alcohol by itself is not very reactive. And so that comes in handy a lot of times. And so the way we do this, there's a number of ways to do it. So there's E1 reactions. You can use H2SO4 and that'll form an E1 reaction, and then you can form your double bond and get rid of your alcohol. Or you can also use an SN1 or an SN2 reaction. So you can use HBr and that'll form an SN1, or you can use hydrogen iodine, and so that will be an SN2 reaction. And at that point, like bromine and iodine are good leaving groups, and they will be able to react more rather than trying to leave your alcohol on there. Okay, so that's pretty much all the old reactions that I want to cover. So this is the new reactions that you guys have learned as of late. So first, I want to talk about your oxidizing agents. And so you can kind of group them into two sections. They're the stronger ones. And so that's chromic acid and sodium hypochlorite. And so you guys, I'm sure, have recognized those before with the NaCl and then the K2Cr2O7 and such. And so those are your strong oxidizing agents. And then your weak oxidizing agents are going to be PCC, DMP, and SWERN. So you guys have, I'm sure, heard of those, and these are kind of what the compounds look like in the case that your professors use the actual compounds as part of the question. And so the main difference between the two oxidizing agent categories is that it really matters when there's a primary alcohol. So for the strong oxidizing agents, they will take those alcohols to carboxylic acids. However, the weak oxidizing agents will take those alcohols to aldehydes and then stop there. It does not matter as much, or it just does not matter when there's a secondary alcohol, but it's very prevalent when there's only a primary one. So as I just mentioned, for like if there's a tertiary alcohol, then it's never going to be oxidized. So no matter what reagent you use, even if it's a strong oxidizing agent, there will be no reaction. However, if we're looking at the secondary alcohols, these will always be oxidized to a ketone. So regardless if it's a strong or weak oxidizing agent, it will be then oxidized into a ketone. And then for a primary alcohol, this is where it's going to make a difference. And that's when you need to pay attention to which oxidizing agent you use in your reaction. So be cognizant of that when you're asked this on your test, because they will have different products. So if we're talking about kind of the big dogs or the stronger oxidizing reagents, it will bring the primary alcohol into a carboxylic acid. But however, if we use one of the weaker oxidizing agents like PCC, DMP, or SWERN, then that will transform the primary alcohol into an aldehyde. And so completely depends on the oxidizing agent. Be aware of this and try to distinguish these. So next I want to talk about Toslate Esters. And so these make OH groups into very effective leaving groups. And so they are very useful for sure. So Tosyl chloride converts alcohol to a toslate leaving group. And so you may have seen this before as in this like symbol OTS. And so essentially an alcohol itself is not a great leaving group. So when it then reacts with the Tosyl chloride, as shown, then it is a great leaving group. And so that is definitely one of the best ways to make an alcohol that was previously unreactive, and now it can react and be a great leaving group. So Toslate esters can be reduced by lithium aluminum hydride to yield hydrocarbon. And so this reduces the carbon to alcohol group to a carbon and hydrogen. And so that is also a great reaction to use when you want to get rid of the alcohol and not replace it with anything. So as you can see, there is an alcohol in the reactant, and then it is then reacted with the Tosyl chloride, and then it forms that OTS intermediate compound, which is then reacted with lithium aluminum hydride, and then it is replaced with a hydrogen. So that is a great reaction to keep in mind when doing synthesis reactions and whatnot. So next I want to talk about the Lucas reagent. And you guys, I'm sure, have heard of this. And this is removing an alcohol using a Lewis acid. And so that's zinc chloride with their hydrochloric acid. And so the summary of the reaction is at the top, where there's a primary alcohol, and then it's reacted with your Lucas reagent, and now it results in a chloride where the alcohol previously was. So that also makes for a great leaving group. And below you can kind of see how the primary alcohol reaction mechanism is different than the secondary and tertiary alcohol reaction mechanism. And so because of that, the rate of Lucas reagent reactions, tertiary and secondary alcohols react faster, and primary alcohols react significantly slower, but that is just something to know. There may be a question asked on that. So next I want to talk about the phosphorus halide. So this occurs for primary and secondary alcohol conversions to alkyl halides. These reactions proceed via SN2 mechanisms, and therefore obviously primary alcohol or tertiary alcohols do not react. So the top is the summary. You can start out with your primary alcohol or your secondary alcohol, and then you'll put your phosphorus with whatever halide you choose. So that could be, bromine or chloride or iodine, whatever you're feeling. And then that will be what the product forms. So your OH group will essentially just be replaced with the halide. And so this kind of just shows the mechanism below. But something to remember, because this is going through your SN2 mechanism, just recall that tertiary alcohols do not react. So that is something to note. Next, I want to talk about thionyl chloride. So this converts alcohols to alkyl chlorides. And so the primary alcohol will undergo the reaction via the SN2 pathway, and then the secondary and tertiary through the SN1 pathway. And so it's quite similar to the reaction I just showed you guys, except the difference is now you can use you can react the tertiary alcohol. So that is a difference for this one. As you can see here, all the alcohols are just essentially just replaced with chlorides. So that is certainly a helpful mechanism as well. So now I want to briefly talk about ester formation. Ester formation will form from carboxylic acids and alcohols together. And so this is a reversible reaction. And so water will react with esters to yield carboxylic acids and alcohols. So in the above equation, you can see how there's a carboxylic acid in the alcohol, which then forms the ester in the water. And because it is reversible, in order to kind of speed along the process, that's when the Dean-Stark reaction comes into play, and I'm sure you guys have heard of this. And so you guys learned about Le Chatelier's principle in probably Gen Chem, and so to drive the reaction forward, the water is removed from the system, and so that's the Dean-Stark distillation, and because of that, that is how you form that ester. So you guys can definitely use that reaction in order to form an ester whenever you're doing your synthesis reactions and such. So more about the mechanism of ester formation. So first off, it's going to protonate the carbonyl and then attack the alcohol nucleophile, and then the proton will shuffle from the alcohol to the hydroxy oxygen. This will then reform the pi bond and lose the water as a leaving group, and then it will deprotonate. And so that is how your ester is formed. So this same esterification reaction can also be done using your H+ ions and then your ET3N, and that's the triethylamine will then soak up the HCl that's released. And so that is also another way to form your ester. Now, if we're talking about ether formation, the best way to do this is your Williamson ether synthesis. And so this is an old school SN2 reaction using an alkoxide nucleophile and your primary alkyl halide or alkyl toslate. And so that is just, we talked about kind of deprotonating your alcohol earlier on. And so this is one of the uses for that. Having your deprotonated alcohol and now your oxygen is going to be a good nucleophile, and then it can then attack an electrophile. And since this is SN2, obviously steric hindrance is not great. So because of that, your electrophile is best off as a primary electrophile. And so with little to no branching, and then it'll undergo the SN2 pathway, and then it will form your ether. So if you guys recall the reactions earlier about deprotonating your alcohol, then this is how you can form your ether. Now I want to talk about your alcohol protecting groups, and this certainly comes in handy if there, for example, is an alcohol group, but you want your other functional groups to react first. Since your alcohol would be the most reactive, if you want to keep that in your compound in a synthesis reaction or any other reaction, then you would want to protect that alcohol first before allowing the compound to undergo its reactions. So first off, you can use your TMS. And so in the above reaction, you can see how the TMS will then react with the alcohol, and then it will form your OTMS. And then later on, after you have reacted the compound, for example, if there was like an aldehyde or on the other end, then you could then react it at this point, and then later on, after the aldehyde has been reacted with, then you can take your TMS off, and then by adding a fluoride ion, and then at that point, your alcohol will return to its original state. So alcohol protecting groups are certainly important if you have other functional groups on the compound that you want to react with first, but you want to leave your alcohol untouched. So that's certainly something that a lot of students make mistakes on because they keep forgetting that if they want to react with something, like that aldehyde I keep mentioning, if they try to react that, it will also react with your primary alcohol. So that is a great way to make sure that you keep that alcohol on there. And I believe that is all the slides I have. And so I will escape out of that. It is Tyler's turn, so if you would like to go now.
All right, so y'all should be able to see my PowerPoint. And yes, these slides will be posted under that YouTube video as well. I'm going to talk about NMR spectroscopy. And so first, we're going to start with the theory. So atoms need an odd mass number so they can have a nuclear spin. So that's why we have Proton Nmr and we have carbon-13 NMR. There are other NMRs like fluorine, I think bromine, but those are rare. For the most part, we use Proton Nmr, and then we kind of like throw in some carbon NMR occasionally. But most of the valuable information is from Proton NMR, and that's why you do all the problems based off of it. So nuclear spin of the positively charged nucleus creates a magnetic field. So what happens is there is no field present. They're spinning all in random directions. When you add a field, you get two different states. You get an alpha spin state and a beta spin state. And you can see that it's aligned against or with the magnetic field. So there's an energy difference between these two. And so in the magnetic field, they will give radio waves and test the energy required to make this flip. And so that is how we are able to probe a molecule structure. So NMR can help us determine molecular structure There's some energy difference between the two spin states. Yep. So shielding is the primary means that we are able to distinguish peaks. So NMR shows us the molecule structure because the protons give signals as a result of their shield. So shielding, I like to think of it as the electrons form a physical like bubble, and the radio waves are trying to attack the nucleus. And so if there's more electrons present, there's more like defenders around the nucleus, and so there's a higher shield. And so when there is a higher shield, it's going to take more energy to cause that flip. So therefore, more energy is going to result in an upfield signal. So down here, I've got downfield is deshielded, upfield is shielded. So the peak locations, these depend directly on where the proton is located within a molecule. So electron withdrawing groups are often present in our molecules, and they will pull electron density across varying distances within the molecule and affect every proton or every group of protons uniquely. So signal location. So I understand that y'all should be in NMR tables on the exam. I think I saw an email containing that. But this is an optional way of interpreting the signal location. I know a professor taught me this back when I took OChem. I believe it's in the textbook as well. But they did this like box method where you kind of familiarize yourself with mainly like the sp3 carbons, the benzene, and the aldehyde carboxylic acid blocks. And you place a signal in its box depending on the atom bound to hydrogen. So look at the examples down below. All of those carbons that I've circled are sp3 hybridized because they've got 4 sigma bonds. And yeah, so once you place it in the sp3 carbon box, the highest it can ever go for ppm shift values is like 4, 4.5. And so once it's in the box, you only have to maneuver it left and right based on its shielding. And that you can kind of do qualitatively. So on this example, we see that a carboxylic acid sp3 carbon, so something that's really close, is going to be heavily deshielded because there's a high amount of electron withdrawing groups in the carboxylic acid. And so we would expect that to be like around 4, 3.5 or 4. Conversely, if we go with a slightly less, electron withdrawing group like chlorine, it will not pull as hard as the carboxylic acid would. And so we have like a 2.5. And so it's about halfway through that box. Then even if we have an OH, which is an electron withdrawing group, this is so far away from the carbon that I have circled that its effects aren't felt. And so these peaks normally are around 1. So usually the ends of your molecules, unless there's like something focused to one side of the molecule, but like a far off end will pretty much always peak around 1. So this is optional. Y'all can use the table and memorize, but occasionally the table values definitely are subject to change. These are a little more, I guess, accurate. So if you find it in an example where you're like, that's not where I thought it would be, know that there is this fluctuation just because shielding really is dynamic depending on the molecule. So signal splitting is where we really get to start piecing together our molecule. So when there are chemically different hydrogens on adjacent carbons, the result is split signals. For simplicity, I know y'all probably practice a lot and you don't need to do this anymore, but you can determine that hydrogens will split each other if they are no more than 3 bonds apart. So if you look at this example molecule, I've said that the orange group and the blue group will split each other because they are 1, 2, and 3 bonds away from each other. However, the blue and the pink are 4 bonds away from each other, hence the green, so they will not split. I'll skip to the end. The n+1 rule determines that the amount of protons in a group that splits another group. So for example, when orange splits blue, the n+1 rule states that there are 3 orange protons. So 3 + 1 is 4. So we would expect blue to show a quartet splitting pattern, which is 4. This is because up here, you can see that an individual proton, and this is the formation of a doublet, So we see that only one hydrogen has two options. It either reinforces the field or it opposes the field. And that actually creates two separate peaks close by one another because the field strength is different. And so going back to the theory, this is all done in a magnetic field, and it will affect the amount of energy required depending on what the nearby hydrogens are doing to the molecule. So you probably don't need to know too much about, or rather any I would expect of the reinforcing and opposing the field. But just in case you wanted to know, that is why splitting arises. So the rules for splitting are splitting occurs vice versa. So if orange splits blue, blue has to split orange. So that's always true. And then alcohols and amines do not split. This is due to rapid proton exchange. So it's easier to see this in alcohols because we actually classify alcohols by their acidity. But essentially, alcohols and amines are constantly detaching from their protons and then reattaching. So therefore, those protons are not fixed. And so for like the frequency that we collect our spectra at, we do not see splitting because we can't account for this temporary bonding of the protons to amines and alcohols. So you will always see alcohols and amines as singlets, and then amines and alcohols do not have an effect on any other hydrogens. So even if it's 3 bonds away, an alcohol proton will not split like another proton because, again, of that vice versa rule. Another kind of random fact that they could show you to kind of help you is sometimes they'll say when the solution was mixed with heavy water or deuterium water, then these peaks disappear. So if they said like we mixed it with heavy water and the peak at 5 ppm disappeared, that indicates that that peak is an alcohol or amine, because when you mix it with heavy water, there are deuterium protons which do not show up on NMR, and they will instead take the place of those alcohol or amine protons. So the next thing we have is complex splitting. So when a group of hydrogens can be split by 2 chemically different groups, the result is complex splitting. So technically, they may have taught you this in lecture, but whether it's a triplet of doublets or a doublet of triplets depends on the J coupling constant. But that is too in-depth for the exam. So they won't, I don't see them asking you to predict a complex splitting, whether it be a triplet of doublets or a doublet of triplets. The most important thing with complex splitting is to be able to recognize when it can occur and then decode it. So complex splitting multiplicity will be noted on the exam. They will say like D of T or doublet of triplets above your signal. And then something that I wrote down here is an example of when complex splitting can come, but you wouldn't think of it, is that double bonds have a fixed configuration. That results in a unique environment around every proton on the double bond. So I know the example that I showed in the bottom right does not have a terminal alkene, but if there was another hydrogen in place of this benzene, this hydrogen would be farther away from the carbonyl than the red hydrogen would be. So you would have 2 separate groups here, which would result in complex splitting for a lot of these protons. For an example of complex splitting, go to the bottom left. We show in the middle that the red proton is nearby. I didn't cross out the bonds, but it's close enough to the green and the blue to be split. It's also close enough to the purple, the alcohol, but because alcohols don't split, we won't see that effect. So really, we only care about the green and the blue's effect on our red proton. And so green is 3, blue is 2, so 3 plus 1 is 4, 2 plus 1 is 3, so it's a quartet of triplets. We can see that hydrogen is split by both the red hydrogen group and the green hydrogen group. And again, this one's kind of tricky. Sometimes people miss this aldehyde carbon because they're not crossing out these bonds. But the result will be a doublet of doublets because there's 1 green and 1 red within proximity to this blue hydrogen. So interpreting spectrums. The first step is typically to calculate your degrees of unsaturation. Know that a double bond or a ring takes 1 degree of unsaturation, triple bond takes 2, and therefore, with that math, a benzene has 3 double bonds and 1 ring, so that's 4 degrees of unsaturation. I like to use this formula. They teach you in the textbook that like nitrogens count for ½ a degree and some other weird facts, but if you can memorize this formula, it definitely helps. Then I read left to right because the most valuable information is often found on the left-hand side. You can instantly see if there is a carboxylic acid or if there is an aldehyde by seeing a peak above 10. You can also see if there's a benzene typically by seeing peaks clustered in the 7 to 8 range. The next thing that I suggest is the reverse n+1 rule. So this definitely helps for complex splitting. So you can interpret quartet of triplets to mean that that signal, as in like whatever signal is being represented by the quartet of triplets, is between a 3 hydrogen group and a 2 hydrogen group. Note the math, like 4 - 1 to 3 - 1. And so you can kind of backwards interpret the complex splitting and place that peak in relation to the molecule. Another tip is to look for common alkane substituent patterns. That's going to be the next slide. And then the last one is when you see a benzene signal, calculate how many substituents you have, and then look at the peak pattern. That will also be shown, part of it. So the common alkane substituents are ethyl isopropyl T-butyl, and these have to be terminal. So just because you have 2 carbons adjacent, if it's like a 3-carbon chain, this pattern will be messed up. So it needs to be isolated. So all these examples are not close enough to anything else to actually split. So we see this pure pattern. So you can see, and I've tried to color code it, that ethyl, you're going to be looking for a triplet that has 3, and then a quartet that has 2. And all the time, the quartet will be further downfield than the triplet because it's closer to the rest of the molecule. An isopropyl group will have this 6 hydrogen doublet and then a 1 hydrogen septet because this 1 hydrogen is next to 6 of the red. So 6 + 1 is 7. And then lastly, if you ever see a 9 hydrogen singlet, that is a T-butyl group. And that's because this bond freely rotates. So all these are the same, they're chemically equivalent carbons. And so they're chemically equivalent hydrogens as well. For benzene, the number of substituents equals 6 minus the number of hydrogens in the benzene region. So I've only done 2 examples here with 2 subs and 3 substituents. And for the 3 substituents, there is a lot of different peak patterns, but I hope the logic of this can kind of rub off on y'all. So looking at this fake spectrum that I've drawn, there are 1, 1, 1, and 1. There's 4 hydrogens shown here. So 6 minus 4 is 2 substituents. And so then you look at the pattern. If there are 4 unique peaks, each with 1, then you have to have a configuration like this. So you need Z and Y indicate 2 different substituents. If they're the same substituent, this messes it up. But y'all should be good by now at identifying unique carbons. But you can just kind of see 2 options that your benzene ring can take. This one is a bit easier because, again, you don't often have 2 of the same substituents like Z and Z. So most of the time, if you see 2 substituents and you have 2 groups of 2, you'll see this splitting with Z and Y because you get a plane of symmetry. Oh, no, it's plane of symmetry here. And you get 2 groups. For 3 substituents, I really only drew 1, but I hope that y'all can just use this and try and draw your options for your benzene ring before you even look at the rest of the spectrum. Now we're on to amine. So amines, there isn't much that y'all ended up covering that's going to be on the test. Most of it is just the synthesis of amines, whether they be, or not synthesis, but alkylation of amines or making primary amines. So to begin, though, we have amine properties. So primary and secondary amines retain the ability to form hydrogen bonds. However, since we do not have as much electronegativity as oxygen, the nitrogen hydrogen bonds are weaker than oxygen. So I know that's a little confusing how I typed it. There's like not the N bonded to H, but hydrogen bonds between nitrogens of separate molecules. So because of that, alcohols will have a higher boiling point because alcohols have stronger hydrogen bonds or stronger intermolecular forces. So they'll have higher boiling points than amines of similar weight and structure. So we can see in this table here, the first one, this does not have an option to have hydrogen bonds because the nitrogen does not have a hydrogen. Same thing with the next one. Oxygen is like alone doesn't have a hydrogen, so it cannot hydrogen bond with a pure solution of this compound. This third example is where we get our first hydrogen bond. And then the comparison really comes between these last two. So we do have the ability to form a hydrogen bond between nitrogens or oxygens, and you can see a very big difference in the boiling points, indicating that oxygens have stronger intermolecular forces as a result of their stronger hydrogen bond. Amines also have a lone pair, and it's capable of donating it to a proton, so therefore amines are bases. So you'll probably see a ranking problem on your exam, ranking by basicity, but just in case they do something else, because I know this was covered in your lecture, this is a reminder of what KB, PKB would look like, and then there's also like a Ka, where you have an ammonium ion where it already has that hydrogen and it wants to give it up. And so you're forming an amine. So just, I guess, keeping that in the back of your head as how these expressions are formed. So Kb is your products over your reactants. But know that a stronger like base is going to be a smaller pKb, or a stronger pK, or a stronger acid is a smaller pKa. So like the smaller your pK values are, the stronger your whatever substance will be. For amine basicity, there's a lot of factors that influence this. Perhaps the strongest is its P character. So it's tried, it was attempted to be drawn to scale, but you can see that, as Khalees said, S orbitals are closer to the nucleus, P orbitals are farther away. So the more P character you have, the farther away this lone pair is and the more accessible it is to a proton. So you can see that a sp3 hybridized amine has a pKb of about 2.88. An sp2 has like pKb of 8, and then an sp is really not basic at all, and it has a pKb of 24. Resonance is going to hurt basicity. So this is a rather interesting observation, but the way I like to think of it is that a base needs a permanent lone pair, because a base is donating that lone pair to a proton. So, for example, this nitrogen has a lone pair, but that lone pair is constantly resonating with this benzene ring. So in a way, this lone pair on nitrogen is less permanent because it's constantly being tossed around this molecule. Whereas a nitrogen that's not in resonance is going to be more basic because it just has that permanent lone pair. And so I know there is another difference of sp3 hybridized nitrogen here versus sp2 hybridized nitrogen here. So that kind of blends in with the P character again. But just think that resonance hurts basicity because you need a permanent lone pair. Electron withdrawing groups hurt basicity. It'll make it a weaker base because they destabilize the conjugate acid. So if you think of your energy diagrams, if you have an electron withdrawing group and your product is going to have a positive charge, that's going to make that positive charge more unstable. So it's going to change that like height of the products on your reaction diagram and affect your overall reaction. Substitution effects. These are electron donating groups. Typically we use like R groups or methyls in this case. Alkyl groups will help us up to a certain point. So we can see that when you compare just ammonia, NH3, to a primary amine. It's a lower pKb because of this electron donation from the alkyl group. And so it's a stronger base. Furthermore, when we add another alkyl group, we get a slightly stronger base as well. When we add a third alkyl group, though, we introduce steric hindrance. And so the proton is not able to approach the nitrogen as easily as it would be for all these other cases. So this is kind of a weird trend, and it's something that y'all can note on your exam. So these are some reactions of amines. The first is going to be alkylation. So when we react the nitrogen as a nucleophile, we can attack a simple CH3 with a leaving group or halogen, and it will attack and kick off the halogen and become a secondary amine. However, when it does this, because of the electron donation, it's actually a stronger nucleophile, so it will attack again. And then it's an even stronger nucleophile, so it will attack again. And so this is an unavoidable process. So it will go all the way, and it's exhaustive alkylation to a quaternary nitrogen. And so usually we try not to do this method unless we want like an ammonium salt for some reason. There is, however, one-step alkylation. And so this is when you take ammonia and you have large excess of ammonia, and you react it with an electrophile with a leaving group. It will only attack once because it just outnumbers the electrophile so much that predominantly you will result in a primary amine. But this is not a perfect method, and the methods shared later are going to be better if you practice them in the lab. So another step of primary amine generation is nitrile reduction. So you can attack it with a nitrile group, so NaCN or potassium cyanide, and it will attack in an SN2 manner, displacing the leaving group. And then you can reduce a cyanide group or a cyano group, or I guess at this point it's a nitrile. When you reduce it, notice that the color code, there is a blue carbon added here and a blue carbon here. So know that if you're doing a synthesis problem, only use a nitrile reduction if you're trying to also add a carbon when you have your primary amine, because you do get one more carbon in your final product. An alternative, if you don't want an extra carbon, is azide reduction. So this is also SN2. It's NaN3. It will attack same way SN2, and then you can reduce it with lithium aluminum hydride, and you will get a primary amine. So like cyanide, both of these can be used as general nucleophiles to like open epoxides or different SN2 mechanisms that y'all did in OChem 1. So this next part is nitro group reduction. So you can occasionally have a nitro group. This is going to be more useful in your aromatics unit when you're actually adding NO2 groups. But for now, you would probably just see NO2 on a molecule already. But you can use a variety of different reagents to carry out this reduction. More often, it's like H2 plus a metal, so nickel, palladium, platinum. Or you can use an active metal and H+, so iron, zinc, and I think it's antimony. And this will reduce it, but I guess this is a more rare example. One of the final ones is Gabriel synthesis. This is going to be how you're going to stop at a primary amine. So you can have any group. This is bromine. I wrote over here can also be a tosyl group. And so as long as it's a good leaving group, you can have this reaction take place. So you need this thalidomide anion. So this is a special group. It will first bond according to this mechanism, and then you have hydrogen and heat, and it will interact around here. I don't think the exact mechanism will be on your exam, but you can definitely check it out in the textbook if you'd like to. But in the end, you do generate a high percentage of primary amine. All right. I think that's it. Yeah. So are there, I guess, any questions? I see the SN is tin. Okay. What's antimony? I don't have to wait for that answer. SB. A lot of tertiary amine would be less available. It's how to make it a better nucleophile. Secondary amine for exhaustive alkylation. That is a good thought. I do remember that strictly for like your SM2 reactions, you really primarily care about the substitution of your electrophile. So I just think that it will still go. I guess I would say, here, I'll back up. When I compared these, relatively, if we look up here, these are all still rather strong bases because they've got a pKb of like 4 and below. And so this will still happen, the tertiary nitrogen being able to accept a proton. But when compared to its other forms, it will happen slower. And so it's a worse base. So with that in mind, you can see, because of this pKb, that we still do get an interaction with a tertiary nitrogen and that lone pair being available, but only when it's compared to the other nitrogens directly do we see that change. And so when we do have exhaustive alkylation, we still will have a strong nucleophile because there still is this electron donation effect from these substituents. And so it will still, I guess, just overcome that steric hindrance and still attack. All right. So with that, I think I will stop sharing, or I'll just start the breakout rooms. So I'm going to start from 8. All right, there's going to be 8 breakout rooms, and I'm going to join one and then bring it back here so it can also be recorded. But your leaders are going to go over the problems with you. Again, if you weren't here for the beginning, we will go through the packet kind of at random. That's because the packet was made rather large so that if you do want extra practice, you can compare it to the key that will be posted later, just as an option for extra practice for y'all before your exam. So we will go until 1:30. But yeah, we will not finish the packet today, or very likely will not finish the packet today. So that is optional practice for y'all. And the recording of this session will be uploaded to YouTube, as well as the materials, whether that be the slides, the problems, or the keys. So I'm going to start breakout rooms now, and then your leaders will join you shortly and begin problems. All right, so we do have 2 hours before the exam review will conclude, but we'll probably take a break about halfway through for just like 5 minutes for y'all to get water, get a snack, whatever y'all need. Goodness, did that ever upload? All right, so here is the packet. We're going to be working through this together, again at a random pace, but yeah, we're going to be going through. I'm going to try and get y'all's input when I can. So the first problem is predict the IR bond stretches that the following compounds will have and determine where this should occur in the IR spectrum. So I guess we'll just do like 2 of them. This is just a illustration to show that we can't predict an exact structure, we can only predict features of a structure. So this first structure with the carbon double bond oxygen, what features of that should we be able to see on an IR spectrum?
There should be a stretch for the carbonyl bond.
Yep. Do you know about where that would be?
Like 1710. Is that right?
Okay. Anyone else have a thought?
1725. Well, I guess that's not including the shift from the benzene. Maybe a
Yeah,
little
so
bit
there
different.
is going to be conjugation. So each conjugation lowers it about like 10 to 20. So I would expect this carbonyl to be lower, probably like 1680 or something like that, 1660. Is there another peak? And you can send like in the chat just the name of the group that we can see, or you can hop on your microphone. So the other group that we should see is a benzene. So this is normally a carbon-carbon double bond, absorbs at 1660, but because there's 3 in conjugation, this is about 1600, and it's very sharp. And so this one we said was about 1680 and 1600. Let's look at the third structure. So what's here?
So that's an amine, so it's secondary, right?
Yep, it's a secondary amine.
So then I think we have, for the secondary, we have a small spike around 3300.
Yep. 33 or 3400. It just depends on, I guess, the location. That's okay. So
Plus
this
the
next one,
29, right? So it's like, it looks like there's 2 humps, one at 33 and then a larger one at 29 for a secondary amine.
I don't know about, I think the 2900 is going to be your carbon-hydrogen bonds for sp3 hybridized. But for the most part, a secondary amine, because it has 1 hydrogen, should just have 1 amine spike at around 3300.
Oh, okay.
And then the amide bond itself, what do y'all know about this? I guess not the amide, but the carbonyl bond. If it was just a ketone, it should be about 1720. Here it's going to be very low, almost like 1640. And that's because carbonyls have resonance possibilities. And for this case, the resonance structure where we have a positive charge on the nitrogen, negative charge on the oxygen is somewhat stable for a resonance structure. So there is a slight competition between these two. And so because of that, I guess the carbon double bond oxygen is not as permanent as it would be in all of their examples. So for that reason, it's much lower, 1640. With that, number 2, y'all can probably do it on your own. We're going to move on to number 3. So this is a ranking problem. Rank by the energy of the bond stretch for the multiple bond atoms. So we're looking only at the multiple bond. Cool. So only the double bond. So I'm going to start a poll with a couple different options for this answer, and then y'all are going to choose what you come up with for your ranking answer. right, I've added a poll. See how I can answer with what you guys get. So we are looking only at the double bond, or I guess the highest. It can also be a triple bond, but the highest peak on here. So for the most part, those will be double bonds, but like for the amide, do not take into account the NH bond at 3300, because it's instructing us to rank by energy of the multiple bonded atoms. All right, so we've got a few responses. For the most part, they are split for the middle three. So all of y'all decided that the first compound is fifth, the last compound is first, so that's good. The first compound just has a double bond, so that's like 1660. And then the last compound has a triple bond here, so it's going to be just less than 2200. For these middle three, though, we are always identifying this carbonyl group. So it should be around 1700, but its location does vary. So a normal ketone is about 1720. And so remember that conjugation lowers by about 20. So I would guess that this conjugated carbonyl is about 1700. We said that the amide group, it does depend and it varies, but this is about 1680. I know I said 1640 before. I think I am, like I was thinking of something else, but there are examples where it does fluctuate. So I would not expect them to pair these two together on an exam because there is some ambiguity as to the order. But an ester is, I guess, the one exception that y'all have learned so far that is higher. So this is around like 1745 is the exact one for this molecule. So it actually goes up from 1720. The way I like to think of it is it does have a resonance form, but I say that the resonance form is a carbon double bond to oxygen. So I guess I think that it's more permanent. I don't know. I know it's not that. Really, it's like some contribution of electrons from this oxygen. But I guess it's a little, it's too complicated for y'all to explain. Just know that an ester is higher. So the final ranking based on these numbers is 5, 3, 4, 2, and 1. Do you have any questions on that? No? Okay. So for number 4, these are synthesis problems. I think the ones, we'll do 2 of these. We'll do B and C. So looking at B, what has happened between the reactant and the product? C double bond C to ketone. Perfect. What's the position of that ketone? If you had to give it like a name. Because remember, with your double bond, you have Markovnikov and anti-Markovnikov. I'll show you why I asked that question. But typically for synthesis, we try and visualize like one step backwards. So we know that this is a ketone. We don't know how to add a carbonyl directly, but we do know how to add alcohols. We've done a lot of examples with that. So we can hypothesize that we have one step before this is this as an alcohol, and then we're going to oxidize. And so if we add this alcohol, what position would it need to be? Anti-Markovnikov. Yeah. So Markovnikov is equivalent to substituted, is the way I remember it. And so anti-Markovnikov is the least substituted side. So we need a reagent that will add a hydroxyl group onto a double bond on the anti-Markovnikov side. Do y'all know of a reaction that does that? Hydroboration. Yep. So that one's going to be your BH3THF, and then There's some other things like NaOH, H2O2, but those are just kind of like environmental factors. The real thing is BH3THF. This will be an anti-Markovnikov addition. So we know now how to get that OH. However, there is a question. When we oxidized the this last step where we've got this compound, we think, and we're oxidizing to form that ketone, why doesn't this group change? It is primary, but typically, if you add an oxidizing agent to a molecule, it will oxidize all spots, regardless, or not regardless, because you can't oxidize a tertiary alcohol. But it definitely can be oxidized, so it will be oxidized if it's there. This was a reaction thrown at the end of Khalees's lecture. It may not have been taught in all sections, but there is such thing as a protecting group for alcohols. Do y'all remember what that is? TMS, yeah. So if we were to react this with TMSCl, we would replace the OH with TMSO, and that cannot be oxidized, it cannot be reduced. And so it's immune to the conditions of the molecule until you remove the protecting group. So I guess now the question is, when should we do that? Do we do it before BH3THF or after BH3THF?
Before, right?
Before, yep. Because if we did it after, we would kind of have competition between these two hydroxyls. So we need to do it before. So I guess our first step is TMS chloride. And then technically you need like N-ethyl 3, just again as like a solution for it. Second we said is BH3 THF. And then the whole purpose of our protecting group was to protect it from being oxidized. So an oxidizing agent. Do we need to care which one we choose? So what's the difference between mild oxidizing agents and strong oxidizing agents? Their effect on primary oxygen. Yeah, so mild oxidizing agents will oxidize a primary alcohol to a aldehyde, whereas strong oxidizing agents will push past the aldehyde and turn into a carboxylic acid. So when you have a secondary alcohol, your choice of oxidizing agent doesn't really matter. So we could use PCC, which is mild, or we could use sodium dichromate, which is a so yeah, we can use either one. So I guess I can do PCC or NaCr2O7. And the final step is removing our protecting group, and we do that with the fluoride ion. So typically we will do like fluoride minus, and then they pair it with the nitrogen butyl 4 positive. It's like a salt, but really you just need the negative fluoride anion. So you can use PCC, DMP, SWERN, NaOCl, all of them. I would say yes. There may be something in DMP or SWERN that I know PCC will do it. I know PDC will do it. But I guess I would have to tell you to check DMP and SWERN. But I'm pretty sure they would all do it. So when in doubt, I guess use a strong oxidizing agent if you can. But if you have a primary, you do need to pay attention to what you're looking for. Okay, so we're going to quickly do C. So this is, I guess, a bit interesting. So we are adding 2 carbons, right? What methods do we know to create carbon-carbon bonds? Grignard, yep, that's definitely one of them. And then another one we'll use, we can use, but I guess I'll show you 2 options. So for Grignard, we need a carbonyl. So we know we're going to need to oxidize this. Yeah. So the other method to create carbon-carbon bonds is to use a Gilman reagent. This might be from OChem 1, but it's an R group. In this case, it'll be CH3, 2, and then copper, lithium. So this reacts with a halogen. It can attack an SN2 faction to create R bonded to whatever the Gilman reagent was carrying. So here inside the parentheses. So that's another one that you can know. But I like the idea for Grignard. So what order should we do these in? I guess it doesn't super matter. But at one point we need to oxidize. So the first thing we could do, we can react with HBr to create that leaving group. We can. Yeah, so we can react with HBr. Another, I would say that HBr is semester 1 or OChem 1. So you would most likely, if you had options for creating a synthesis, which I guess told there could be, well, PX3 or phosphorus with 3 halogens is a reaction from this chapter, and it replaces OH with whatever this halogen is. So I would say if we did PBr3, we could create this compound. And then after that, we can use the copper lithium. Creating this. However, at this point, we've run out of our alcohol, right? So this reaction chain does still work, but we're 1 carbon short. So if you haven't identified it, what we first need to do is oxidize it. And we do a mild oxidation to create an aldehyde, because you cannot use a Grignard reagent with a carboxylic acid, because you have an OH there and it will ruin the Grignard. We can then do MgBr, CH3. It will attack once, creating this compound. Then we can do everything down here. Y'all see that difference? Knowing that Grignard results in an oxygen or an alcohol, we can edit our order to go Oxidation, Grignard. We replace the OH with a leaving group, bromine, iodine, chlorine, and then we do a Gilman reaction. Just for y'all's info, I guess one other option is that technically a carboxylic acid plus, and I don't know if they taught you this, but that SOCl2 reagent will also replace this OH group here. So you can create acid chlorides like that. And then you could do a Grignard times 2. So that is another option. But the first option is more in tune with the unit y'all have been doing. But again, for your exam, they could give you a bunch of choices, like A through M of reagents, and say choose the right order to do a synthesis. But yeah, synthesis is definitely something they can still do even on a multiple choice exam. So it does help to think kind of backwards, like we did on the second example. So what's on this next page? I'm gonna save this one for y'all because it's another, it's a reaction chain. This is another type of question that I guess could show up on your exam, whether it be spelled out like this and they're asking you to identify each compound, or whether it's just arrow after arrow after arrow. But these are reactions from your alcohol unit. So let's look at IR. So number 6, we are given 3 IR spectrums and 6 different compounds, and we're asked to match these. This is definitely something that could show up on your exam because it is picking from multiple choice and you're just matching. So this first one, I know it is small. You do have the capacity to zoom if you go to viewer control in the top right corner, right underneath the, it's like a magnifying glass on top of paper. What do y'all see in this spectrum? Broad peak above 3,000. Yep. So it definitely is wide. What is that usually indicative of? Yep, it is an alcohol. So I can annotate our document, say that this is an OH, alcohol. So I guess there's 2 options. We can continue to look at the spectrum, or we can look up above. The structures with an alcohol are B and D. So our only job now is to differentiate between B and D. So how do we do that? B has a C triple bond C. Yep. And then D has a alkene, C double bond C. Where does C triple bond C show up and where does C double bond C show up?
Triple is below 2200, right?
Triple is below 2200. A nitrile C triple bond N is just above 2200. But because, I mean, you can see it on here, it's really hard to see exactly where it is. So hopefully they would be nice to you and not have like a nitrile group here as well. But we can see, I'll just say a double bond is 1660. So here's 1500. So 1600s are out here. We don't see anything here. So there's no double bond. We do see a alkyne, and that's around 2200, because here's 2000, so 2200 is here, so it's kind of between there. There isn't a question whether it's internal or external, but we can also see, usually in OH, I've heard it described looking like a tongue because it has a very rounded bottom. This one has a very sharp peak. So this is actually a CH bond SP hybridized. So this is this hydrogen. So with that, the first one is B, because we eliminated D based on the fact that this doesn't have a double bond peak, and then we confirmed B because it has an alkyne peak, and then the alkyne is terminal. So what about number 2? What can we see about that spectrum? Huge carbonyl peak. Yep. So that's right around like 1700. So the carbonyl, if we look at our options, we've got a classic ketone and we've got an aldehyde. So how will we differentiate between a ketone and an aldehyde? Aldehyde fangs. Where are those located? $27,000, $2,800. So 2,700 is here, 2,800 is here. Are these aldehyde fangs? I know I just covered them up. There, moved them. Are those aldehyde fangs? This is, I guess, a tough example because they're kind of minor. But on a test, you will have to choose yes or no. The answer is yes, those are aldehyde fangs. Typically, if a peak is kind of like isolated from itself, when you see carbon hydrogen, which kind of interferes with aldehyde, they're usually very long, but sometimes they can be short. But they are going to be completely separate from aldehyde. So know that if you do see something over here and they are sharp and there's 2 of them, those are aldehyde fangs, no matter they're like positioned up or down on the y-axis. So if this is an aldehyde, I missed it a couple times, but this is an aldehyde. I guess I'm used to seeing that hydrogen there. But the middle compound is going to be E. The final compound. What do we see here? Another carbonyl spike, no fangs. Is there a structure up there that fits that? C. Yeah, so we did eliminate E, but I guess in the event that you were stuck and you decided to move on to the next one, you could see that these are the only two carbonyl-containing compounds. And if we had to make a comparison between the aldehyde fang regions, we could clearly see that there are aldehyde fangs for the middle one, and there are not aldehyde fangs for the third spectrum. So good job. Like I said, these can be given to you on an exam. There's one other example on another page of this packet that has multiple spectrums and you're matching. So I would just kind of do what we did, where you pick a feature, whether it be an alcohol or whether it be an aldehyde, or not an aldehyde, a carbonyl, and then you look at the potential structures and try and narrow your choices down. That way you can know what you're looking for on the spectrum. Because we told ourselves by looking at B and D that we just had to look for an alkyne or an alkene. And so that will make your exam easier. Oh, this is the next one. There are 4 spectrums and 8 molecules. So I guess this one's a bit tougher, which is why I left it for y'all for additional practice if you'd like additional IR practice. This one's interesting. This is the first example that we have of NMR for this packet. But this is another option where we consider a reaction. Compound A with a molecular formula, react it with chromic acid to obtain compound B. We react compound B with reagent C in acidic conditions to obtain product D. It gives you HNMR and IR, and then it gives you carbon NMR and IR. So where do we start? Okay. B has a carboxylic acid. And I guess we could expect that because CrO3 is a strong oxidizing reagent. But I guess that also tells us that A must be what? Primary alcohol. So yeah, we expect that this is going to be a primary alcohol. So what's the first step that we do when we solve an NMR spectrum? Splitting first, usually. Yeah. But sometimes the first step is to calculate degrees of unsaturation. So we do have a formula. C6 or C3 H8O. So degree of unsaturation formula is 2 times carbon plus 2 plus nitrogen minus hydrogen minus halogen over 2. So for our example, we would have 2 times 3 is 6 plus 2. We've got no nitrogens. We've got 8 hydrogens. We've got no halogens. So it's going to be 0 degrees of unsaturation. So that means we don't have any double bonds. We don't have any rings. So we can look at splitting, and I guess there should be splitting here. There will be on your exam. So I'm going to tell you that the goodness. All right, so the 2 here is going to be a triplet. The 1 is a singlet. The 3 is going to be a triplet. And then this 2, which looks like a multiplet, is going to be a quartet. That's a G. Quartet of triplets. So I guess for this one, I can walk y'all through how I like to solve these. And then in the future, y'all can offer, I guess, thoughts based off of this. So one thing I mentioned in the lecture is when I do see complex splitting, I like to do the reverse n+1 rule. So these 2 hydrogens right here, we are saying that if it is a quartet of triplets, and that's 4 of 3, and so that means that that red group is between 3 hydrogens and 2 hydrogens. So if I were to draw a carbon, I would put 2 red hydrogens, and then I would say that there needs to be something with 2 hydrogens and another bond to something with 3 hydrogens. Do y'all understand that? So just from that quartet of triplets, we are able to kind of solve for a chunk of the molecule on itself, because that has to be true. Because amines cannot, amines and alcohols cannot contribute to splitting. If it's between 3 and 2, like it's between a carbon with 3 and a carbon with 2. And because we know we don't have any degrees of unsaturation, we don't have to worry about double bonds or anything like that. Lastly, we do have this 1. And I said that this is a singlet. I know it's a little messy and it's kind of hard to see. What's this 1 singlet? OH. Great. So we know that it's OH. And so I guess the last thing to do is just attach it. And I hope y'all can see. And I guess NMR can be almost a guess and check. And so we're going to say that based off of what we've done, we've got this structure. We've got 3 carbons in a row and then an alcohol. So if we look at that, that would make these 2 hydrogens directly adjacent to the alcohol, which is why they're super de-shielded. The red hydrogens would be complex split, as we kind of decoded by the orange and the green. And then the orange hydrogens would be the farthest away, and they should be down here. And then if we look at the multiplicity, orange is only split by red, and there's 2 reds. So we would expect orange to have a triplet, because 2 + 1 is 3. And then if we look at the red, it's between 3 and 2. So we'd expect a quartet of triplets, which is what we had. And then green is only next to red, whereas things that can split it. And so green is also going to be a triplet, because 2 reds + 1 is 3. So this is a structure. So for A, and I can draw it again above A, we've got that, 1 propanol. So when we react it with chromic acid, we oxidize it. And when we oxidize, we don't change the number of carbons, we just change the bonding to oxygen. So we get our carboxylic acid, correct? So B looks like that. C and D are another mystery. What can we see from the IR spectrum from D? We do have a carbonyl. Do we have a carboxylic acid anymore? No. I would ask you if there's aldehyde fangs. These kind of look sharp, but these are not aldehyde fangs. And then technically we are missing a peak here. Maybe it's because they want you to look at the carbon NMR. But another great thing, and I mean, y'all do have your tables, but if you remember from the presentation, I said that like this was aldehydes, like above 9 and 10. About 7 to 8 is benzene. And then up until about 4 is sp3. And then alcohol is a lot wider. I didn't memorize carbon NMR values because I was taught that this pretty much supersedes directly below. So we can almost draw benzene, sp3, aldehyde, carboxylic acid, stuff like that. There's minor variations, but that's as much as I knew, and it got me through. But what we can tell is there are peaks here that belong to a benzene, correct? And I guess if you looked at your tables, I would expect benzene to belong from 120 to 140 shift. So they do not have a benzene peak on this IR for some reason. It should be around 1600 and be pretty sharp. Not as sharp as the carbonyl like I drew it, but pretty sharp. So if we are adding a benzene, I guess we could have also looked at the formula, which is C9H10O2. If we did degrees of unsaturation, we're going to have 18 plus 2 minus 10 over 2. And so that's going to be 5 degrees of unsaturation. So 4 is with our benzene. So that means we have 1 left. So what's a reaction that y'all know with carboxylic acids and we introduce something else, say a benzene ring? That's okay. So we need to introduce a benzene ring. If you notice, between these two, I guess if we made a formula for B, because I don't just want to tell you the answer. If you do run into a trouble like this on the exam, C3H321H6O2. Oh, that's acetic acid. Wait. Yeah, I think. Maybe. But anyways, if we were to do the math, we have added 6 hydrogens, or not 6 hydrogens, 6 carbons, and 4 hydrogens. But I guess the hydrogens don't super matter, but we do realize that they've only added 6 hydrogens, or carbons, which means that they've only added the benzene ring. So I would suggest that a solution to this would be an ester, where we have a benzene ring attached to that oxygen. If you calculate the formula, it will be C9H10O2. So what I did with that formula, C3H6O2, by finding out that there was only 6 carbons that were added, I know that this group is only benzene, and that it's not something like O and then an extra carbon and then a benzene ring. So what would that make C? If that's what D looks like, what type of reaction is this, and what would that make C? So this mechanism is called Fischer esterification. And the H plus is going to activate the carbonyl, making it prone to attack. And so all you need for Fischer esterification is a carboxylic acid and an alcohol. So if we have a benzene ring with just an alcohol, then when we protonate, the benzene ring is able to attack. Ultimately, like it also protonates the water to make it a good leaving group. There's a lot of things that go along in the mechanism, but we basically get like a switching and a formation of a ester. So this is an important reaction to know. It's the only esterification reaction that you know. If you want to make an ether, what you would do is Williamson ether synthesis, where you would react an alcohol with a very strong base like NaH, sodium hydride, or NaNH2. I don't know the name for that one. And it will deprotonate, making O-, which can then attack SN2 style on a halogen leaving group. So forming an ether, which is an oxygen linkage within a molecule. So the ester is this functional group with a carbonyl directly next to an ether. My screen went black. Can anyone else see? Okay. That's fine. You can come back. And because we're in this main room, I won't need to move you. But we can move on. These are the second half of the problems. These will be over Nmr and Amines. So I guess the ones that I want to do for this ranking, I think the only ranking question that I want to do is 11, which is ranked by basicity of the nitrogen. The other ones are Nmr questions. These should be valuable for y'all to do on your own. And the key does spell it out rather detailed why the ranking is the way they are. But I would say do number 11, ranked by basicity of the nitrogen. So before we do this, do y'all remember what like the most important thing for nitrogen basicity is?
It was a lone pair, right?
Yep, it's the lone pair. P character. Yeah, so hybridization. So it's all about the lone pair. Do we want the lone pair to be close or far from the nitrogen?
We want it close.
So if it's trying to give the lone pair away, we're going to actually want the lone pair to be farther away, because it's almost reaching out like farther. The molecules don't have to get close enough to each other, or the atoms don't have to get close to each other to form that bond. And so if you think of it as like an extended giving hand, you want that lone pair to be far away. So with that in mind, we have sp3 greater than sp2 greater than sp. And that ranking is solid, like a strong majority of the time. So I don't think everything else is like intra-category. So like within sp3, we then get inductive. We then get resonance and other things to consider. Or I guess we can't have resonance if it's sp3. But within these categories, we have other factors, substitution as well. I guess that's also inductive. So if hybridization determines it, do y'all remember, are electron withdrawing groups good or bad for basicity? Electron withdrawing groups are bad. Do y'all know why? That's okay. So if I have destabilizes the conjugate acid, exactly. So chlorine bonded to carbon, bonded to nitrogen. I'm not drawing hydrogens. If we were to react this as a base, we would get chlorine, carbon, nitrogen, hydrogen, positive charge. This chlorine would pull electron density toward it, thereby making this positive charge unstable. So conversely, electron donating groups should help basicity. But again, only to a certain point, because if you compare like substitution, there's a weird trend. But that doesn't really come into here. So with that, I think y'all can rank this. I guess I'll leave these up for a second, and then I'll erase it when I write down the answer. But I'm again make another poll, and y'all can answer with your ranking. All right, I think I've given y'all enough time. Looks like y'all are torn between two choices, so that's good. I'm going to clear what I wrote. So first thing that we need to do is assign hybridization. So this nitrogen is sp3, sp2, sp2, sp3, sp. So remember, these two nitrogens in the middle are sp2 hybridized because they have a lone pair and they're next to the benzene ring. And so if it's next to an sp2 molecule or atom with a lone pair, it becomes sp2 hybridized as well. Or you could ask yourself, can it resonate? It can move down and cause a bunch of resonance structures. So those are sp2 hybridized. So with that, we can pretty much instantly say this was number 5, sp. And then we should say that the first and the fourth are number 1 and number 2, respectively. And then these two are 3 and 4. And that is again because of their hybridization. So now we compare. So benzene is an electron donating group. So it is highly electron rich. It's got a giant cloud of electrons around it. So it will donate. But I guess that's not as important as the presence of this fluorine. over here. That is an electron withdrawing group, so we do have a dipole in the molecule going toward the fluorine. So if we remember, we said electron withdrawing groups destabilize the conjugate acid, therefore making it a worse base. I would expect 1 and 2 for the rankings. Then, if we compare these middle two, the only difference between them is NO2. Is NO2 a electron withdrawing group or electron donating? That's what NO2 looks like for reference. So NO2 is an electron withdrawing group. And so it is neutral, if you can see what I've drawn, because the positive charge and the negative charge of oxygen and nitrogen, or nitrogen and oxygen respectively, cancel each other out. So it's a net neutral molecule, but because of octets, because of everything, this is what the group looks like if you drew it out. So because this nitrogen has a positive charge, it wants electrons. But it can't have them because this oxygen wants to give electrons, but you can't break, I guess, the octet of nitrogen. Nevertheless, though, this is an electron withdrawing group. It's a very strong electron withdrawing group. When you guys get to your aromatics unit, you guys are going to probably memorize. The professors will want to say, like, deduce, and you can deduce the general trend. But NO2 is among the strongest electron withdrawing groups that you'll encounter in your aromatics unit. So that makes 3 and 4 for these rankings, because the presence of NO2 again creates a dipole going toward the nitrile group. And so that is our ranking: 2, 3, 4, 5, 1. Does anyone have any questions? Great. So we've got 45 minutes left. I want to take just a brief break from talking, so I'm going to give y'all like 3 minutes till 12:50, and then we'll resume with the next problem. Okay? So that way y'all can do whatever you need to do, take a break, and come back. But 12:50, we'll resume. So I am back. So this first one, we are now on to interpreting Nmr spectrum. So, do y'all remember what the first thing that we do with Nmr spectrums to solve them? There's a formula involved. Degrees of unsaturation. Yep. So, if y'all remember that formula, how many degrees of unsaturation do we have? The formula is 2 carbon plus 2 plus nitrogen minus H minus X. That's okay. And then all of this is over 2. So I guess one way to remember it is find some acronym to remember for NHX, whatever you might remember for that. But if we did that, 2 times 7 is 14, plus 2 is 16. No nitrogen. If we subtract the hydrogen, 16 minus 5 is 11. We have 1 halogen, that's chlorine, so 11 becomes 10. 10 divided by 2 is 5 degrees of unsaturation. So we would expect benzene, because we've got over 4 degrees of unsaturation. Yep, we do see there is a benzene here, because this is 8, and this is a really hard axis to read, but this is 7. And then we've got 1 other double bond to take care of. So then I say read left to right. So if we do that, the first peak we encounter is at 10 ppm, and it's a singlet with 1 hydrogen. Can y'all identify that? If it's above 10, they can be one of 2 things. That's going to be a carboxylic acid or an aldehyde. And it's going to be that hydrogen that's in the carboxylic acid, so OH, or it's going to be the hydrogen that's directly on the aldehyde. So in this case, which one does it have to be? I think it's an aldehyde. I would agree. If you look at the formula again, we've got C7H5O. Yep. So it has to be an aldehyde. So this is, and we can even draw it. You know that it's R, H, there we go. And it is a singlet, so I guess it means it's far away from other things because an aldehyde can have signal splitting. But we'll figure that out later. To continue, do y'all remember what I suggested to do with the benzene? That's okay, I can remind y'all. With benzene, it's helpful to know what your benzene ring looks like. You can look for symmetry, yeah, but we can find out the number of substituents by just finding the number of hydrogens that are in here. So 6 would be, if it was just a benzene ring, every carbon had 1 hydrogen on. If we then subtract 4, because the 4 comes from 2 plus 2, we get 2 substituents. So we know that our ring is going to have 2 groups that are bonded to the ring. We can then look at the signals. So we've got 2 groups of 2. So that means that we do have symmetry, correct? Because every hydrogen should be unique because it's on its own carbon. So the only way you can have a group of 2 on a benzene is if you have some type of symmetry. So if you also remember from the lecture, I gave 2 options for this. One is going to be, probably shouldn't put X, but X usually means halogen, but that's an orientation where it's the exact same substituent in those positions. That's going to be ortho, you'll learn that later. But that would create 2 groups of 2. Another option is, I'm going to use Y and Z, where you have different substituents in a what's called para position. That would create 2 that are closer to Z, 1 bond away, and then both 2 bonds away from Y. So you would get here and here are 2 hydrogens, and then here and here are 2 hydrogens. So that is 2 groups of 2. So I guess I say that to make things interesting, they don't want to give you too much symmetry. So often I would say you're going to have this case with Y and Z, 2 opposites. But another way to figure that out is to say, well, I know benzene has to have 6 carbons. And I know there's 4 hydrogens on the benzene. So if I calculate what I've kind of solved for by just knowing what benzene has, we would do C7H5OCl minus, and that looks like a 2, 7, minus C6H4, that's what we've solved for. We're looking at carbon with 1 hydrogen and chlorine and oxygen. That's all we have. 4 atoms, a carbon, hydrogen, chlorine, and oxygen. So that kind of means that we can't have the same group, right? Because in order to have an X and an X or a Y and a Y, you would need to have like components left over that you could duplicate. And then we go back to already having solved for the aldehyde by seeing that aldehyde signal. So we then know that our H double bond O, that eliminates the carbon, the oxygen, and the hydrogen. So all we have left is a chlorine. So I hope y'all can see the answer. Now, we're going to have a benzene ring with a hydrogen with a chlorine. Does that make sense? I can put the red hydrogen here, and then if I wanted to, I guess these would be green hydrogens, and those would be, if I had to guess, those would be here. And then the blue hydrogens would be here. And I would guess that signal's here. And I only say that because we've got 1, 2 bonds to chlorine, whereas if we do the other one, we've got 1, 2, 3 bonds to oxygen. So I don't really know the difference between these, but it's going to look something like this. You won't be asked to designate something ambiguous like this, which signal belongs to which hydrogen. But you can check, and you will see that it will be 2 groups of 2. They will be doublets, because remember that you only count the things that are adjacent on a benzene ring. So this hydrogen is technically only adjacent to 1 of the hydrogens from the green group, and so split the signal accordingly. Both will be doublets. All right, so I'm going to leave the next one for y'all. Do you have any questions over this Nmr spectrum? So problem number, oh, I guess I never numbered it, but here's another one. It's a different style spectrum, because finding spectrums online is hard. But the first thing we do is what? Unsaturation. If y'all remember the formula, does someone want to guess how many degrees of unsaturation we have? 5 is a good, probably not a guess, probably remembered it. We've got 18 plus 2 minus 10 over 2 is 5. So again, we would expect a benzene, and we've got a double bond left over. So now we look at the spectrum. So we read left to right. Here's our benzene region, 7 to 8. What does that tell us about the benzene? Two types of hydrogens. So by the peak, we would expect that, but I did put overlapping multiplet. So that means that there are signals that are so close to each other chemically that their shift value is kind of on top of each other. So it's a mess. So really, we don't know how many peaks are here. But if you remember, with benzene, we can find out the number of substituents by doing 6 minus number of hydrogens equals number of substituents. So in this case, it's 6 minus 5 equals 1 substituent. So we are looking for a benzene ring with a single substituent up top. So I will tell you that as a result, we get a group here, we get a group here, and we get a group down below. So there's 3 groups. So that means that the black and the purple are represented here because they're far away from Y. They don't really feel the effects, and so they are very similar chemically. So now that we have a picture of what our benzene looks like, we only have to solve for Y and then connect to the benzene ring. So another thing that I mentioned is be very familiar with your common alkyl chain or alkyl substituent groups. One of them is shown here. If you have a 2 hydrogen quartet and a 3 hydrogen triplet, and the quartet is further downstream than the triplet, chances are you're going to have a specific substituent. It's an ethyl, yep. So we should be expecting, can't use red. There's green, There's yellow. So we should be expecting R. 3 yellows, 2 greens. That's an ethyl because they're adjacent to each other. The 3 yellows split the 2 greens, creating a 2 quartet. The 2 greens split the 3 yellows, making a 3 triplet. So great, we know that we have an ethyl group. However, if we kind of take a roll, I guess, we know that what we've accounted for so far is all of this. So that is C6H5. We've solved for that. We've solved for Y yet. And then we also know that somewhere there has to be an ethyl. So that's C2H5. So if we were to add those together, we would have C8H10 is what we solved for so far. So if we take C9H10O, we find out what we're missing. We are missing a carbon and an oxygen, and a degree of unsaturation, because there is 5 degrees of unsaturation. We've only solved for 4 of them with benzene ring. There would be a ketone. I don't know if you're able, depending on your device, but do one of y'all, I mean, it is anonymous if you try and draw. Do any of you want to try and draw solving for Y? What we would expect to see? All right, someone did draw that in black. And do you all agree? Is that the answer? We completed this with a benzene ring. So we're looking for a benzene ring with 1 substituent. We've got that. And then we are looking for an ethyl group that's isolated. Can't be split by anything else. That's right there. And then we've got carbon with a double bond oxygen. We find that that is where it is. Yep, splitting the ethyl has to be unchanged, taking into account the OU. Yep. So this is the answer. So if you learn, there's lots of practice online for NMR, if this comes difficult to you. But this skill is definitely something that comes with practice, 100%. So these tips do try and make it easier. I love the benzene tip because it solves a big portion of it for you. I guess I'm not the biggest fan of the math down below. That kind of helps, it kind of doesn't help. But I'm just trying to explore, I guess, everything that might help you. And then the rest, I guess, is just practice and logic. So if you are struggling with it, peer tutoring will be open before your exam for like drop-in tutoring. So y'all can visit and ask questions or whatever. But I would tell you that it does come with practice. IR most of the time comes with like recognition and then I guess memorization. But because you're building a structure with NMR, it does have a lot of practice involved. So we're going to skip this next problem. Y'all can do this on your own. This has a high emphasis on NMR and then a little bit of IR mixed in. Because we have 20 minutes left, so I think we can do number 14. And then maybe one of the last ones, and then we'll be done. So number 14 says, use the following spectra to solve for all reaction components. So really it just is NMR again. We first need to solve for A. A has a formula of C8H10O. So If we do degrees of unsaturation, does anyone know how many that is? 4. Good job. So 2 times 8 is 16, plus 2 is 18, minus 10 is 8, divided by 2 is 4. So we'd expect a benzene. We do have one again, 7, 8. It says 5 overlapping. The first time I saw this, I guess my professor hadn't stressed the fact that they could be overlapping, and they didn't give us overlapping. They just put 5 above it. And I was upset because I did not know any situation where there could be 5 in one peak. And I think it was on a quiz or something, but it was a lesson I never forgot, that benzene, because it only has one substituent, everything else is relatively far away. So especially if you have a group attached to benzene that isn't very electron withdrawing at all, these will overlap on your axis. You can zoom in and differentiate them maybe, but I will tell you that if you take Nmr spectra, you rely on the computer to do all this integration. Sometimes the computer cannot distinguish peaks at all. So it will just take the total integral underneath it and give you the volume, which is 5. I will tell you that Dr. Seibert has some funny stories, I think. He mentioned back in the day, before the computer would automatically integrate for you, they used to have to take scissors to print out the spectrum as big as they could. They would then take out the scissors and cut as close as they could along the peak, and then weigh it, and then divide it by a standard, and they would say like 1 hydrogen equal, I don't know, 0.0002 grams of paper. And so that's how they would do Nmr spectra before the computer could integrate for them. So that's just a little tidbit. But with benzene, we'll do 6 minus 5 equals 1 substituent. Again, we're dealing with, that's not a very good benzene, with this type of shape. And now we need to look at what we have remaining. So of these 3 peaks, one of them kind of stands out. Does anyone want to take a shot at what that is? You could also take a clue from the reaction process. We are reacting A with Tosyl chloride to get B. So what should we expect to find in A? There's an alcohol. So of the 3, which one's going to be the alcohol? The 1 singlet. Yep. So this should be our OH. So that means these other ones probably bind together because it all is one substituent, but we need to solve this. So we could also reverse n plus 1. We could circle this and say that 3 hydrogens are next to, and then 2 minus 1 is 1 hydrogen. We could also see this one, we've got 1 hydrogen is next to 4 minus 1 is 3. So with that, what do we guess? These are next to each other. So the 1 hydrogen from the blue group splits the 3 hydrogens in the green group to form a doublet. And the 3 hydrogens in the green group split the blue hydrogen to form a quartet. But we also have to throw OH in there. Then secondary alcohol. So if we drew this with that as the final structure for A, would you all agree that that's how it looks? We would have the red hydrogen here. We would have the blue hydrogen. And then we would have the 3 greens. I don't want to draw that many hydrogens. So that is A. So I'm going to write it smaller or closer to A. If A is that, what happens when you react with Tosyl chloride? Replace ROH with ROT. Yes, technically it's ROTS with Tosyl. But yes, this is going to replace OH, and you're going to make O and then TS. I guess I wrote it backwards, so it could be ST. I don't know. If I wrote it like this, it'd be ROTS is how it's normally done. So this is now a leaving group. So what type of reaction is step 1 of this next process? Does anyone else agree that this is SN2? C+N with a minus, that is a great nucleophile. It is going to attack. The leaving group is OTS. So it is SN2. So it will come and it will attack here. Initially forming, I'm going to move the location just to make it. I just kind of rotated the molecule so I can fit it. But that is what we get. What happens when we do LAH with a nitrile group? If you don't know, you can look at IR spectrum compound C for a hint. We're going to get a primary amine. So LAH is a reducing agent. Sometimes it can react with things like triple bonds and reduce them to single bonds. So what it will end up forming for compound C is that. So an important distinction is that there is a carbon here from that cyanide group. And so we have replaced OH with an amine by first reacting with Tosyl chloride. We also could have done PBr3 and changed it to a bromine to make it a good leaving group. We Tosyl chloride. We attacked it with SN2 with sodium cyanide. SN2 attack displaced it. We've got the blue compound. When we react it with lithium aluminum hydride, we reduce it to form a primary amine. Cool, cool. What's going on in the 1400 to 1600 range on the IR? Good question. So there is a benzene, and then technically the cutoff for what we can determine is 1500. So I would say I don't know what this peak is. Maybe it's carbon, single bond carbon. Probably not. Probably not. I don't know what that peak is, but I do know that this is benzene. And then these, as y'all recognized, are primary amine. Spikes, teeth, fangs. That's about it. We're going to move on to the next page. So I'm going to do the first one and the third one. So for the first one, I'm going to first ask y'all a poll, and it's going to be yes or no. And what you're answering is, will that product form after these reactions? Which number? Oh, 15. Sorry. So I could definitely see them asking you this on an exam. I think a question like this shows up on a PLTL packet if you're in PLTL. Should be for this week before y'all's exam. So those are made by your professors. So if they're thinking of these type of problems for PLTL packets, I would say that this could be an easy true-false question, kind of. But as you can see, I've also asked, like, explain what steps went wrong, correct the sequence. They could do this on an exam. Probably easier for them to do this than it would be synthesis. But in a way, it's kind of the same thing. Because if it didn't form, they could ask you which step went wrong. PBr3, Mg, CO, whatever that is, or sodium dichromate. Number 17. So I was trying to, so I've got some answers, 2 yeses and 1 no. So 2 of you think it will form, 1 of you thinks it won't form. The answer is no. And there's one spot where this process fails. A carboxylic acid is formed instead. That is true. So this is a strong oxidizing agent. I'm trying to separate that. Strong oxidizing agent. So if I were to draw this all the way out, PBr3 is going to make Br, and then we're going to make MgBr, and then it's going to attack the Grignard once, forming, because there's 1 extra carbon here that was here, and then ultimately, oh wait, I added 2 extra carbons. I apologize. I can't erase that. Just scribble that out. 1 extra carbon here and here, and then sodium dichromate should turn this into carboxylic acid. So what do we need to fix it? What should we replace sodium dichromate with? PCC would do it. Yep. So would DMP. So would Swern oxidation. Cool. So now let's look at number 17. So I wrote, there is a mistake in the following sequence where 1 reaction will not occur. Fix the sequence and then draw the correct product. So I guess I'm going to create another poll asking which step do you think will not occur? Or I guess I should ask, instead of not occur, I should ask which reaction will result in no reaction. So 2 of y'all have chosen the first step, sodium cyanide. 1 of y'all have chosen the alkylation. Think first, because OH is not a good enough leaving group. Do y'all agree with that? So the first is a SN2 mechanism. You need a good leaving group for the reaction to occur. It will not occur with an OH. So we can put like an X through here and put no reaction. So now I want to fix the sequence. What's the only thing that we're missing here? We're missing a good leaving group. You could tosylate before NaCN, or you could also use Br3, zinc Cl2. Yep, that would put a chlorine there. So yeah, we just need to convert it to be a good leaving group. So I'll do the TSCl. We'll make OT, that's supposed to be capital T, S. And then we can do sodium cyanide. That will create, and then what is, and then LaH creates, and then CH3I. Oh, we're missing a carbon there. Correct? What does CH3I do? So NH2 is a good nucleophile, so it will attack. And then an electrophile is CH3I. So I guess if I drew out the mechanism, we're saying that the lone pair is going to attack, making the iodine leave. Forming that. Does that look correct? So if you hadn't heard of the reaction, then that's fine, but there is one important thing to know about this last step. And this is just alkylation. And if you go back to the slides for the reactions that I showed, I told y'all that after it adds once. This is an even stronger nucleophile. So whenever you see CH3I, they can't even really say one equivalent because it's hard to do single molecule. It's impossible, really, to do single molecule experiments. You need like solutions. So even if it's like 0.00001 molar, it's still rough to make it happen. So this is exhaustive alkylation. So the answer that I drew was wrong. It's going to keep attacking this group until it cannot attack anymore. So I know I've almost run out of space. I'm going to choose a different color to make it obvious. Black. There we go. So that is the product of 17. If we fix the first step by adding Tosyl and then let the rest of it go, we're going to end up with a quaternary nitrogen because we've exhaustive alkylated it or something, and we end up with that. So do y'all have any questions? If not, y'all are free to go. Thank y'all for coming. Thank y'all.